Okay, everyone. Last week I talked about the basic equations of control. I also talked about control of steady state error system type 0, type 1, type 2. Any question? No? If I ask you what's the type 1 system, anybody knows? Okay. So, again, I assuming everybody knows. This week, I will continue control of steady state error system type for subject to reference and disturbances. And not this week, next week I will finish the chapter about the basic properties of the feedback by discussing control of dynamic error using PID control system. But it's going to be for the next week, not for this, not today. Today I will just finish the topic of control of steady state error or system type. What I discussed so far in terms of the type of the system was for the unity feedback system. What is a unity feedback system? What's the unit feedback system? When do we have a unit feedback system? Okay. Unit feedback system is when we assume our sensor is very accurate and it has very fast dynamic response. In this case, and with assumption that the gain of the shaping block and sensor is the same. In this case, we have the unit feedback system. But in reality, most of the systems are not unit feedback system. If the system is not unit feedback system, what we have talked about so far is not applicable to such system. So we need to redefine the subject or topic of system type for such system, or systems having a block diagram block in the feedback of the system. As I'm sure you're not remembering, we assume in the feedback we have a transfer function hy over hr, which y was the sensor transfer function and hr was the shaping transfer function, input shaping transfer function. As I said, because we have block on the feedback is not anymore unit feedback, and we need to redefine the concept of or the formulation of type of system type for such system. If you remember, we defined transfer function h in feedback as the ratio of hy, sensor transfer function, over input shaping transfer function as a h, and hr, the closed loop, the control transfer function, as block D. Do you remember that why we have the HR D closed loop and HY over HR from the previous lecture? Okay. Just one head is nodding. Okay, good. But it's good to review your lecture notes before coming to the class. It's good for you to understand the new topics. As I said, we have this block transfer function in the feedback. We need to see how we can define the system type for such closed loop systems. There are two possibilities. One way or one method is to reshape or restructure this closed loop system as a unity feedback system, or develop the formulas for this case. Let's talk first about how to reshape or restructure this closed loop transfer function, this closed loop system, feedback system, as a unit feedback system. Do you have any idea how we can do that? How can we restructure this closed loop block diagram as a unit feedback closed loop system? If you remember, for the unit feedback system, we have a straight line here. We don't have this transfer function here. So let's see how we can restructure this block diagram as a unit feedback system. What we can do, look, this is the transfer function we have here. We have a sensor function, transfer function in the feedback. We want to reshape it to the unit feedback system. In other ways, we want to remove this block in the feedback so that we can use the previous relations we developed and definitions we define for the system type of the unit feedback system. What I do, I add a unit feedback system, a unit feedback to the system and subtract from this transfer function. If you rearrange all this, the first or inner loop feedback, and consider as an open loop of the system, you will have a unit negative feedback to the system. How does it work? If I reshape the loop gain or loop transfer function. What was the loop transfer function definition? Loop transfer function. Okay. The transfer function from the input to the feedback before closing the feedback of the system. Okay. For example, if you start from this point and calculate the loop, you will have the loop gain as a DGH. Okay? But here, I need to simplify this inner loop, closed loop system, and just keep the unit feedback. If I do this, I will come up with this loop gain or loop transfer function. How can I calculate this one? Let's show you. Okay. Just consider the inner loop transfer function or block diagram. I have a control transfer function D, system gain system transfer function G, and H minus 1 here. And here. I'm just considering the inner loop closed loop system. Okay? In this case, the transfer function will be dg over 1 plus dg h minus 1. Okay? So, what we'll have, if I put everything here, the system will be in this shape. Let's do it here. I will have summation Vg 1 plus Vg h minus 1 and a unit feedback. So I have a unit feedback. My open loop or loop gain will be dg1 plus dg h minus 1. It will be type 0 if I have a constant steady state error for a step input. It will be type 1 if I have a constant steady state error for a ramp input. It will be type 2 if I have a constant steady state error for the parabola input. Correct? What was another definition of the type? The number of integrator of loop gain. If I don't have any integrator, what was the integrator? Was 1 over S. If I don't have any pole at origin for the loop gain of the system or loop transfer function of the system is type 0. If I have just one integrator, the system is type 1. If I have two integrators, the system is type 2. So, in this case, if transfer function dg over 1 plus dg h minus 1, I have one pole at origin, the system is type 1. If I have two integrators, the system is type 2. What was the purpose of the defining the type of the system type? What's the usefulness of having system type? No. To have an idea about a steady state error of the system without calculating closed loop transfer function. Just to look at the open loop transfer function, for example, here, if it is unity feedback, DG, I look at the DG. If DG has a pole at origin, if it doesn't have any pole at origin, it's type 0. It means for the step input, I have a constant steady state error. If I have just one integrator or one pole at origin, it means the system is type 1, and for the step input, a steady state error is 0. But for the ramp input, I have a constant steady state error. Okay, so it gives us the truth without calculating the transfer function of the system, closed loop system, and just by looking at the loop transfer function to see if there is any steady state error for a given input or not. Okay? Any question? But what I'm talking about so far is with respect to reference. I'm assuming the disturbance and noise from sensors are 0 because of the superposition principle. So, if I have this loop transfer function, the error of the system will be 1 over 1 plus L. L is the loop gain of the system, or loop transfer function, multiplied to R. R is the reference input to the system, which will be equal to SR. What was the S? Okay guys, seriously I'm getting worried. I'm getting worried. You need to read your lecture notes. S is the sensitivity transfer function. The sensitivity transfer function is 1 over 1 plus L. L is the loop transfer function of the system. Okay. But is another way to calculate the steady state error of the system. Why do we need to calculate this? What's the reason that steady state error is always so important to us? Why we are concerned about the steady state error? What's the definition of the error? Reference and output. We want to have minimum steady state error or 0 steady state error in order to have a perfect trajectory. In fact, the output is exactly the same as input to the system. Correct? So lower steady state error, better response in terms of the tracking the input. That's why we always looking in terms of the basic or classical control system, we are looking for the error, minimizing the error or approaching error to 0. But we can define the error of the closed loop system, which has a transfer function in its feedback using a complementary sensitivity function. What's the definition of the complementary sensitivity function? 1 minus S, sensitivity transfer function. Why do we call it complementary sensitivity function? We can see from here. Wait. Okay. From the block diagram, the system transfer function is, here is the, again, the closed loop system. D is the control block diagram. G is the plant transfer function, and H is most probably sensor transfer function in the feedback. If I calculate the closed loop transfer function, Ys over Rs will be dg 1 plus hdg. If you look at your lecture notes from last week, do you have your lecture notes from last week? Do you or not? Okay. Guys have the lecture notes, shows the guys don't have the lecture notes. Okay, share with them. If you look at the lecture notes, you have the lecture notes on the last one. Oh, yes. If you look at the page number, I don't know what's the page 4 of the handout, the second slide. There is a definition of the sensitivity and complementary sensitivity transfer functions. What? 4? The middle one. Okay, page 4 of the lecture note, middle slide. If I have H, the complementary sensitivity transfer function will be dg over 1 plus H dg. And according to the definition of error, which is reference minus output, will be Rs 1 minus tau s Rs. If I factor out Rs from this relation, I will have Es equal to 1 minus Ts Rs. 1 minus Ts is sensitivity transfer function. That's why we call it Ts as complementary sensitivity transfer function. Because it's 1 minus Ts will be equal to S. Okay? Any question? Look, this is just a definition. If you know the definition before coming to the class, you will understand what I'm talking about. I don't have time every lecture to review the previous lectures. As I said before, I know control is boring for majority of you. I don't say all of you. But if you want to make it more fun, this module, you need to ask me question. I answer your question. But if I don't get any question from you, I don't know which part is understandable to you, which part is not. So please read the lecture notes before coming to the class. Or at least watch the videos. I don't know which one is much easier for you, but watching the videos won't take you 1 or 1.5 hours before coming to the class. Okay. So, we assume that the condition of final value theorem are satisfied. What's the conditions of final value theorem from lecture, second lecture? What? Louder. What? No, this is the definition of final value theorem. What is its condition?
Opposing views on left hand plane.
Exactly. All pole should be in the left hand plane. If we have even one pole in the right hand plane, the final value theorem is not applicable. So when we say that the conditions of final value theorem are satisfied, it means all poles are in the left hand side plane of the complex plane. So with this assumption, we can apply the final value theorem to this error relation. A steady state error will be limit of Et when t goes to infinity. Based on the final value theorem, it is equivalent to limit of S, E of S when S goes to 0. And we saw that E of S for the closed loop system with the block diagram in transfer function in the feedback will be 1 minus tau s rs. So this, if we calculate this limit, we will have, if we have the any type of the polynomial input, will be s1 over s power k plus 1, 1 minus t tau s. Why s k power k plus 1? We can represent the basic input of the system as a 1 over sk plus 1. For example, what's the transfer function of the step input? 1 over s. Ramp input 1 over s squared. Parabola input 1 over s cubed. Okay, so that's why we can show any input as a 1 over sk plus 1. I show it as a sk plus 1 because s power 1 will be cancelled out with this s, and I will have just 1 over s over k. So the steady state error, if I do this calculation, I cancel s with 1 of s of this polynomial, I will have a steady state error as a limit of s1 minus tau ts over sk plus 1 when s goes to 0, which will be equal to the limit of 1 minus ts over sk when s goes to 0. What do I want to get from this relation? What I'm doing? No idea. I just told you. We are interested to calculate the steady state error based on the system type. System type is based on loop transfer function without calculating the transfer function. Here, in the previous lecture, we developed different type definitions for the closed loop system with unit feedback system. But here, today, we have a block diagram or transfer function in the feedback of the system. So those relations are not applicable. We are looking for developing a relation for such system which has a block diagram or a transfer function in the feedback. So steady state error will be calculated in this form. By this, if we calculate steady state error, we can have three cases. Steady state is 0, steady state is constant but not 0, and steady state error is infinity. Depends which case we have, we can define a type for the system or system type. Okay, let's see what we have. If the solution of that steady state error is a non-zero constant, this is the definition of the type. The system is referred as type K if we have non-zero constant steady state error. As I said already, if k is 0, which means we have type 0 system. If k is 1, we have type 1. If k is 0, and by definition, the steady state error will be 1 over 1 plus kk. What was the definition of this? The name of this steady state error? It was position constant error. Again, if you look at your previous lecture note, last week I defined the definition of position constant error. Okay, if I have the type 0. If I have type 1, the steady state error will be in the form of 1 over kb, which is the type 1 system, and the name of kb is velocity steady state error. From last week again. So again, what we have defined last week for the position steady state error, for the velocity steady state error, or acceleration steady state error, all were for unit feedback system. Here today we are talking about the system with or non-unit feedback system. For the non-unit feedback system, we need to look at the steady state error of the system, and based on the number of poles at origin, we can define the type of the system. Okay? Any question? No? Okay. So let's give you an example to see how does work these definitions. In this example, I'm looking for the system type for a servo with tachometer feedback. What's the servo? Have you heard ever about the servo electric motor? The electric motor, DC electric motor that have the controller inside the motor. So, yeah? Yeah, it automatically controls itself. Okay? Have you heard about the tachometer? What's the tachometer?
Sensor that measures the rotation speed.
Rotation speed. Yeah. Tachometer is the sensor that measures the rotational speed of the system, of a motor, usually. Where did you hear about that? What?
In cars.
Which course?
No, in cars in general.
Oh, okay. Okay. I think you have heard about this one in the instrumentation and.
We've used them.
No?
Yeah, we used them.
Experimental
Okay. Yeah. Okay. But if you, I don't know how many of you are aiming, but next semester, not this year, next year, I will give a mechatronics module. In mechatronics module, I will explain everything all sensors you've taken already. Okay, so assuming we have the electric motor and we have a tachometer as a sensor in the feedback in order to measure the rotational speed. Assuming that the transfer function for the plant, here our plant is the electric motor, is given by 1 over S tau S plus 1. And the controller is a simple proportional control, Kp. And the transfer function for the tachometer is 1 plus Kts. We want to see what's the type of the what is the system type and what will be the error of steady state error of the system if I have a tachometer in the feedback. Okay, you tell me, how can I calculate this one? How many methods do I have to calculate? How many? Which approaches do I have to solve this problem?
The one we've just done, the equation we just derived,
Yeah. One is that one.
and
Another one?
actually derived the whole transfer.
Exactly. I just explained to you. Two methods. Restructuring the transfer function as a unit feedback system or calculate directly the steady state error of the system from scratch. Okay? So let's see how we can solve it. Solution. Let's choose the second method. Calculate the steady state error from this. The steady state error we calculated is limit of S1 minus TSRS, which TS is dgs1 over 1 plus HDGS. We have the formula for H, D, and G in the example. If I substitute H, D, G, I will come up with this ratio here. Look, D was a constant proportional gain, Kt. Gs was 1 over S tau S plus 1. And H was 1 plus Kts. If I substitute all in this relation, I will come up with this ratio. The input is in the form of the polynomial input, a general form. If k is 0, I have the STEM input. If k is 1, I have a ramp input. If k is 2, I have a parabola input. If I calculate this steady state error, which means I put S equal to 0, this one is 0, this one is 0, this is 0. In the denominator, I have just Kt, and in denominator, I have just Kt as well. So it will be 1. Depends what's the number of k, I have different steady state error. For example, if k is 0, this S will be cancelled out with this S, and I will have just 1. Am I right? This is 0, 0, 0, 0. Yeah, I will have just 1. If k is equal to 1, I will have 1 over S. So steady state error will be infinity. Correct? Is that clear? No? Okay, which part is not clear? Ask me.
No, it's just
You lost, totally lost?
It's just too late.
What can I do? Okay, at least you can review the video at home when you refresh. Okay, again, if k is 0, steady state error will be 0. Steady state will be 0. I think I'm missing something here. This S will be cancelled out with this S. And this will be 0, this will be 0. Kp. Oh, sorry, I made a mistake. Look, if I put S0, this one is 0. This bracket is 0 as well. Here I have just Kt. This one is 0, 1 multiplied to Kt. Here S0, 1 minus 1, 0 will be 0. So it will be 0 over Kt. Okay, if k is equal to 0, this this S will be cancelled with this denominator S. So will be 1 by 1 multiplied to 0 over Kt, which will be 0. Okay, if k is equal to 1 or bigger than 0, if k is equal to 1, I will have 1 over S here, 1 over S, this will be cancelled out, this will be 0. Let me see, this will be 0. I will have Kt, if k is 0, if equal to 1. It will be 1 over S squared, S will be cancelled out with this one, will be 1 over S. S tau S plus 1 will be 0. This one will be 0. This one is 0. What will happen? How can I get the 1 plus Kt?
That S was cancelled. The S was cancelled.
Which S is cancelled?
K is equal to 1.
How did I solve this one? Let me see. 1 plus. Okay, in denominator I have Kp. Oh, yeah, correct. No, I figured out how did I solve it. Let me. this one is 0, I will have 1. 1 minus 1 will be 0, will be kt. Kp s, and here 0, 1 plus kt s kp. Okay? This s will be cancelled out with this one, and this s will be cancelled out with this. I will have kt kp in numerator. This one is 0. I will have kp. So again, 1 is missing, isn't it?
The S should be cancelled with the denominator S.
Yeah, you're right. You're right. I made a mistake. So let's let's do it here. I have, let's put tau s squared plus s plus kt kp s over tau s squared plus s plus kp plus kt kp s. This s will be cancelled out with this s. If I factor out s here, I have s tau s plus 1 plus kt kp, and from the denominator I will have tau s squared plus s plus kp plus kt kp s s1 over s squared. So this s will be cancelled out with this one will be cancelled with this one. I will have, if I put the s equal to 0, this one will be 0. I have 1 plus kt kp. Here this one 0, 0, 0, kp. Correct? Yes. Yay. So, if k is 0, SADSZ will be 0. If k is equal to 1, I have the SADSZ error of 1 plus KP over KP, which is not constant, which is constant, non-zero. Okay? If I have k bigger than 1, the SADSZ error will be 0. It will be infinite. So, because for the k equal to 1, I have a non-zero constant error, the type of the system is 1. Okay? System type is 1. And the velocity constant or velocity constant error will be kp over 1 plus kt kp. Why kp is kp over 1 plus kt kp? If you look at the lecture notes from the last lecture, last week, you will see the definition of the kp is 1 over a steady state error, which will be kp over 1 plus kt kp. Okay, look at here. Kt is a property of the sensor, and usually always is bigger than 0. The velocity constant is smaller than the unity feedback value. In fact, Kt for the unit feedback system is 1. Okay? If it is 1, if I have the Kt bigger than 1 or bigger than 0, the value will be bigger than unit feedback system, which means that if I use a tachometer in the feedback as a sensor, I can improve the dynamic response of the system, but the steady state error will increase. So it's a conflict between what you want to do and what you will achieve. In some cases, maybe it's not in this case, in general. Sometimes it's much cheaper for you to have the tachometer rather than, for example, position sensor. You need to have tachometer, or you can get a better dynamic response. What do you mean? What do I mean by better dynamic response?
The correction of the feedback loops.
the system can respond quicker to changes in input?
Can be less overshoot,
Oh,
lower raising time, faster raising time, lower settling time, depends what we want to say. Okay? But usually if using the tachometer, I can get better dynamic response. I can reduce the overshoot, for example. But for sure, I will increase the steady state error of the system. If steady state is not important for me, that's fine. If I just want to improve the dynamic response of the system, that's fine to use the tachometer. But if I just want to have the proportional controller and steady state error is important for me, I can use the tachometer. If I want to have, for example, absolute zero steady state error. Okay? Any question? No? So, let's summarize what we have talked about. I have talked about last week and today. Before summarizing, let me explain to you something else. Look, so far I talked about the system type with respect to reference. So what does it mean with respect to reference? I assume disturbance and noises are zero. Okay, I just focus in terms of the tracking of the input when the disturbances are zero. But in reality, we have many types of the disturbances. Fortunately, we can estimate or approximate the disturbances to the system by a polynomial input, such as ramp, step, parabola, or other type of the polynomial inputs. If I have a disturbance, which steady state error is most desirable to me? Zero. Why? Because what was the definition of the disturbance signal? An unwanted signal. It will deteriorate the response of my system. I want to reject it as much as possible. Right? So we need to check how much the system is robust against the disturbances, or how much a steady state will be introduced to the system subject to a disturbance. Again, I have the steady state error subject to the reference. I have the steady state error subject to the disturbance. The overall steady state error will be summation of these two steady state errors. Why? Give me an answer. If it is one, don't be shy. Why? Because of the superposition principle. Correct? Because of the superposition principle. It will be summation of those. I can tolerate it if the steady state error due to the reference. But I can tolerate the steady state error due to the disturbances. I want to reject it. So we need to look for or look at the transfer function from the output to the disturbance input. We need to define the type system type with respect to disturbance input. So far what I have talked about, it is the system type with respect to reference. Now on, I want to talk about the system type with respect to disturbance. I will ask you these questions in your final exam. I will ask you both qualitative and quantitative questions. Okay? Because I want to make it interesting to you. So wake up. Wake up. I will ask you both qualitative and quantitative questions. So, again, by knowing the system type, we can have idea what will be a steady state error of the system subject to a given disturbance input. The transfer function from error to disturbance is equal to minus ys over ws. Why? Why? If any of you can answer, I will give you 25% of your coursework.
Zero.
What zero? Y es over ws is equal to minus ys over ws. Okay, I increase it to 30%. 35. 10 minutes? No, it's too much. Because it's so simple. 40% is the last one.
What was the question again?
Good one. Why?
Is it because of the like little transfer function errors?
What?
Is it the little transfer function errors? If you input WS.
Why? E is error over disturbance
If the output over input
is equal to minus y over ys over ws. Two more minutes.
The output equals the input when you have feedback.
You are close, but not correct.
Do I get at least 20%?
Okay, guys. Go.
Because we,
let's go. Okay, the error transfer function gets from error over WS. Like the trend is. I have this in my mind. I can visualize it right now.
Okay, guys.
It's because it's
Negative
the other.
is it because R is zero?
Opposite of
What?
Is it because R is zero?
Exactly.
Oh,
You got 4%. Oh! Your name is Robin, isn't it?
Yes.
Okay. So, Robin, you have the 40% of the euro.
What the
Yeah.
The input function.
Why did you tell me that? What's the definition of the error? It's Rs minus Ys over Ws. Because I'm talking about the, just talking about the disturbance, according to the superposition principle, I can put R equal to 0. So Rs is 0, which is equal to minus Ys over Ws. So simple. Well done. So, I defined. Oh, you didn't get it? Seriously? ES is what? Is the difference from the input or reference signal and the output signal. Okay? I'm talking about the disturbance response. Because, look, if you look at the lecture notes, we have 3 inputs, R, W, and V. If I want to talk about the response subject to each input, according to the superposition principle, I can put the rest of the inputs 0. Here, I have Rs and Ws, but I'm looking at the Ws. So I put Rs equal to 0, according to the superposition principle. So the transfer function will be equal to minus Ys over Ws. Okay. So In similar way as for reference inputs, the system is type 0 if the step disturbance input results in a non-zero constant. It's type 1 if for the ramp input I have a non-constant error. Again, 40%. No, it's much. 20%. 20%. For type 1, what's the steady state error for the step input? Not you, Robin. You are out.
Do we get 20% on the course?
20% on third floor.
1 over S squared.
What?
1 over S squared.
No. Steady state error for the type 1 subject to the step input. Steady state error.
0.
You need to give me reason. So you can't say 0 or non-constant or infinite.
So 0 is the answer.
Because
The first one. Who's talking? You.
Because k is equal to 0.
What in red cake?
When you have here, when you have this comma s in the
It's not so. Okay, the answer is 0. Why? Why is it 0?
Gain to 0.
it's a ramp function.
1 over S.
How many numbers do you know?
If it's a type
Raise your hand. Raise your hand. What?
What exactly is the question?
Why? For this type of 1, steady state error is 0 for a step input function. A step input signal.
Doesn't reach
Okay, guys. There is. If you have type 0, it means for the step input, you have the constant steady state error. If you have type 1, it means for the step is 0 steady state error. For the ramp is constant. For the higher polynomials is infinite. If you have type 2, it means for the step and the ramp, you have the 0 steady state error. For the parabola, you have the constant non-zero steady state error. For the higher, you have infinite steady state error. Okay? Is that clear? Yes. So hopefully everybody woke up. Okay. What time is it? What's the time?
56.
What? 56? Okay. So okay, guys. I will finish it next week. To be honest, I wanted to finish this lecture slides, but it looks like you're not ready for that. So please be ready next week.